You should now understand what tasks and task networks are. But I explained to you earlier that for this approach to planning, we really need three new things: tasks, task networks, and methods. So that's what we will be looking at next. And while we look at methods, keep the following in mind. We again try to set up our planning problem as a search problem, and methods describe ways in which we can transform task networks. They are plan refinements and therefore correspond to state transitions in our search space. I will start with the formal definition of an STN method. And the first thing we need to define methods is a set of symbols that we can use to denote these methods, to name these methods uniquely. These symbols will be disjoint from all the other symbols we've used, so unlike task symbols which overlap with the operators, they will not intersect with the other type of symbols. Then an STN method is a four-tuple, which means it consists of four things, and these four things are the name, the task, the preconditions, and the network, and I will explain those in turn now. The first component is the name of the method, and the name is a way to refer to this method. And again, we will use a syntactic expression which looks very similar to the type of syntactic expression we've seen for tasks and operators. It's a symbol n, which must be one of our unique method symbols, followed by a set of parameters x1 through xk here, which are variable symbols that occur in M. And again, these parameters describe the objects that are manipulated by this method. The next component is the task of this method, and that is simply one of the non-primitive tasks that we've described earlier. The task of a method describes what can be accomplished with this method. And of course, it must be non-primitive, as all primitive tasks can be accomplished by an operator. But if we have a task network that contains a primitive task, that is, the task of a method, then we can use this method to accomplish the task in the network. The third component of a method are the preconditions associated with that method. And again, like for an operator, this is simply a set of literals that we need to achieve before we can apply this method. So when we apply a method, these preconditions need to be true, they need to hold in the state where we apply the method. So they are very much like the preconditions of an operator. Note that there's no effects associated with a method, so that distinguishes an operator from a method quite significantly. And the reason for this is that in this approach to planning, we are trying to accomplish tasks rather than achieve goals. So we don't need the effects, we need the task of the method to do planning. The fourth and final component associated with the method is the network of the method. This is simply a task network consisting of tasks and edges, which are ordering constraints. And the tasks in the set U are called the subtasks of this method, and you can think of this method as breaking down the task, the second component of the method, into the subtasks that make up the network of the method. So the task of the method describes what we can accomplish, this is what we accomplish, and the subtasks, or the network, describe how we can accomplish that task. And there may be different methods for the same task, but achieving the task in different ways by having a different network, and usually also different preconditions. Methods, like task networks, can be totally ordered or partially ordered, and that is simply a property of the network associated with the method. So if this network is totally ordered, then we say the method is totally ordered. If this network is partially ordered, then we say the method is partially ordered. So essentially, you can think of a method as breaking down a task, the task the method accomplishes, into subtasks represented by the network. In the next few slides, I'll simply show you some examples of STN methods. And these are the same methods I've described informally earlier for moving a stack of containers to another pile, respecting the order. And I'll start with the simplest method from that example, namely moving the topmost container, and that was simply a take action followed by a put action. And the first thing we have here is the name of the method, which consists of a method symbol, take and put here, and the parameters, of which there are quite a few. And these parameters are, of course, all the objects that we need to perform the two actions. So I'll go through this. C is the container that we're trying to move. K is the crane with which we pick it up and put it down. This all happens at location L. And then we have the pile in which the container is originally and the pile to which it is being moved. Then we have XO and XD. These are two containers. XO is the container from which we're taking the container that we're moving. That's C. And XD is the destination container onto which we're putting this container. So these are all the objects involved in the take and put method. The task we accomplish with this method is simply described here, and that's a task as we've described earlier. So we've got a task symbol followed by the parameters of the task, and these are only the two piles from which we're moving and to which we're moving. And to be able to apply this method, we have a number of preconditions that need to be satisfied, and you should be familiar with this notation from the way preconditions were described for operators. So the first precondition was that the container that we're moving is on top of the origin pile. Then it needs to be on the container from which we're taking it. The pile needs to be at that location, and the crane also needs to be at that location. Also, the destination pile needs to be at the location, and the container onto which we're putting it, our container C, must be the top of the destination pile. And then finally, we have the subtasks, the network associated with this method, simply consisting of the two primitive tasks, take and put. So we're taking with crane K at location L container C from the origin container in the origin pile. And then we need to put the container with the same crane at the same location, the same container we just picked up, onto the destination container in the destination pile. These are the two subtasks of this method, and as you can see, I've described them as a sequence, so they are totally ordered, which means this method is totally ordered. Next, I will describe two methods for accomplishing the task of moving the whole stack. Remember, this moving the stack reverses the order in the containers. And the informal description said that moving a stack can be accomplished by repeatedly moving the topmost container until the stack is empty. And as you know, repetition can be achieved through recursion, so I first define a method, recursive move, which takes four parameters, namely the origin pile, the destination pile, the container we're trying to move, and the container from which we're moving it. And the task that we accomplish with this method is to move a stack from the origin pile to the destination pile. Remember, for the previous method, our task was to move only the topmost container. Here we move the whole stack. And there are only two preconditions associated with this method, namely that the container that we're trying to move must be at the top of the origin pile, and it must be on top of the container XO from which we're trying to take it. Then we have two subtasks that we need to accomplish the task of moving the stack. And the first subtask is that we need to move the topmost container. And then we have a recursive call, so to speak. Namely, we have the task that this method achieved as a subtask. So we need to move the remainder of the stack from the origin pile to the destination pile after we've moved the topmost container from the origin pile to the destination pile. And again, the subtasks here are totally ordered, so this is a total order method. But we have a second method described here, and that is the no-move method. And let me start with the task this time. The task for this method is the same task as before. So here we have move stack from PO to PD, and here we have move stack from PO to PD. These two methods accomplish the same task. But the two methods have different names and they have different preconditions. So previously we needed a container that is on top of the origin pile, and now our only precondition is that the pallet is the top of the origin pile, which is another way of saying that the pile from which we're trying to move the containers is empty. And if the pile that we're trying to move, the stack of containers, is empty, then the subtasks are also empty. That means there's nothing that needs to be done to move 0 containers from one pile to another. So the first method we've described here implements the loop of moving the containers repeatedly through recursion, and the second method makes sure the recursion bottoms out. The final example then is for moving a stack via an intermediate pile to make sure that we maintain the original order. So the first move reverses the order, and then the second moving of the stack reverses it again, means we have the original order back. And to accomplish this, we have a method very cleverly named moveStackTwice, which takes three parameters: the origin pile, the intermediate pile, and the destination pile. And the task that we accomplish with this method is to move the stack in an ordered fashion, move ordered stack, from the origin pile to the destination pile. And this method is always applicable, which we can see here. It has no preconditions, so as long as we can find values for the three parameters, we can apply this method. And the network associated with this method is again totally ordered. It has two subtasks, and the first subtask is to move the stack from the origin pile to the intermediate pile, and then we move it from the intermediate pile to the destination pile. So it's again a totally ordered network, which means we have a totally ordered method, which means all our methods were totally ordered.